Seabird 198, when localizer established, descend RS.
Once established on localizer, descend RS, 21.
Seabird 198, could you give me a wind check, please?
Showing 240.
Descent at 5 miles. Hotel at 65845 hours. Oh, 186, thanks. Target on Jack 6584 with you at ILS 15 and contact. Down, leave it. 2525. And you're okay. Turn on the taxi, I suspect it might be the risk. You've got 7 miles taxis. Channel 6584 is with you.
Channel Express Air Services is a leading European cargo airline. Operations started in 1978 using Herald aircraft. These were progressively replaced through the 90s with the Fokker F-27 500 and 600 series. These aircraft are quicker and quieter than the Herald and carry approximately 6.5 tons. In 1991, Channel Express introduced the Electra, a 4-engined aircraft able to carry 15 tons at 360 knots. The next step was the pioneering one of converting Airbus 300 aircraft to the freight role. Channel Express operate 3 of these. They are able to carry approximately 45 tons and, most importantly, have a volumetric capacity of 350 cubic metres. This enables the aircraft to operate both for the express parcel services, which is an increasingly important business, as well as interlining with the major airlines. And today we're operating a regional service for Finnair from Helsinki through to London. The next thing to do is to join the crew on the aircraft where it's rather warmer. We'll make our final preparations for the first hour or so flight to Göteborg.
Paikki Ville Tukholmasta ja tulisi paikkaan 20. Ville jatkat Rovaniemelle 12.10.
So first section of the day, so full briefing, might take off up to 100 knots, shout stop and I'll stop between 100 knots and V1, advise me and I'll make a quick decision, and it's quite a long runway and it's quite a high V1. After V1 any malfunctions, make sure the plumbing heads safely, we're coming up, cancelling any noise rather please, 600 feet to reconfirm any problem, and if we have a separation, mechanical failure or fire, and ask you to carry out the drills and Richard will monitor your progress in that. 1600 feet to accelerate, and there's an emergency bit here which is basically follow the sea and turn right blue next to the 10 that's due to obstruction out in the distance.
Clocks.
8:23, 3 miles.
23.3. Compasses.
Slave synchronized cross check.
Slave sync cross checks.
Altimeters.
1001, cross check.
1001 set cross check.
Spoilers.
Ja rämpille aamupäivät.
Radar on tree.
364 Maikia.
Ja ykkönen se reitti on 503.
Oxygen mask interphone equipment. Check. Engine is is complete with exception of the de-icing. Fluid service 65,000 VMO pointers.
So we'll be ready to call for start very soon. They're just checking there's no start restriction for us.
There is no restrictions for you, so are you ready to copy clear?
FM go.
Connect 6585, clear to Gothenburg, follow Runen 3 Bravo departure route, airway November 872, squawk 3665, information Victor, Genes 1001. Connect DSA.
Channel 6585 will take off to Runen 3 Bravo, November 872, the squawk.
The and anti-icing is completed with side 1 and side 4 fluids, side 4 hold over side.
On. Engine 2.
All pressure riding.
blue.
Transponders, DV, both on. Cabin navigation lines. Right, clear radar. On. Retake objectives. 1 o'clock, sorry.
N1 SRS. I'm the first officer today operating the A300 with Ed and Ralph. I'm just going to give the approach brief for Gothenburg, which is where we're heading to at the moment. This is the initial arrival, what we call a plate for Gothenburg, and you can say it's for runway 03, and it's got an effective date and labelled H1, and all 3 crew members would ensure that we're looking at the same plate before we do a brief. Typically we'd start from the top. We have a transition altitude of 5,000 feet which relates to pressure settings. We then have a number of different notes which really are warnings or guidance. For instance, number 1 on here talks about intercepting the localizer, which is to make sure we're on a straight line for the runway, and we must intercept that no lower than 3,000 feet. And there are a number of other items, most of them are fairly standard, things like maximum 250 knots below flight level 100, that type of thing. Right, air traffic control have told us that we've been cleared to do the Maxim 1 Echo arrival, which as you can see is this one here. We're coming via a position Maxim, which is 72.6 miles from the Backer VOR. And we track 214 degrees magnetic into the VOR, and we then turn left onto 162 degrees, and we continue around, having reached a position of 221 degrees from Landvetter VOR, which is a ground-based beacon, and we turn inbound to pick up the 025 to come back in towards the runway. Things of note, the safe sector altitude within 25 nautical miles, and we know to the west our clearance altitude is 2,600 feet, and to the east is 3,200 feet, and we would only go below those altitudes when we're under positive radar control, or in fact if we're visual with the field. Then go on to the actual approach plate, if I can change plates. Okay, this is the approach in more detail but closer up to the airfield. Again, we can see this is for an ILS or an NDB approach for runway 03. On the previous plate we saw that we turned inbound to a track of 025 degrees to line us up with the runway, and here we can see this is where we pick up the 025 inbound. Now, apart just from the plan view, we've also got a profile which shows us a procedural approach. So in fact, if we come in from above this beacon, we can descend from whatever level that we are at going over the beacon on a track of 205 to 3,000 feet. And 3,000 feet, if you remember, was the minimum altitude we were allowed to maintain before locking onto the localizer. We would then, if we do a procedural approach, fly over the beacon, come back round and fly back again in the opposite direction towards the runway, and we could descend at this descent point, which in fact we're going to do an ILS approach today. So the ILS will actually guide us from this point on a 3-degree glide slope all the way down to the runway. Now we've got a check altitude at this beacon here, which is called an outer marker. It's delineated by the Sierra Lima NDB of 342, so we would dial that on some of our instruments, which we can show you in a minute, and that would show when we've gone over that beacon, and our instruments would, the needles would drop as we go over. As we're descending towards the runway at that beacon, we have what we call a final approach fix, and we must make sure that we are at 1,680 feet as we go over that beacon to make sure that we're on the right profile. We then descend down to our minima for this particular airfield, which I'll get in a minute for us. Thank you very much, Ralph. So we can go down to 680 feet is the lowest we can go down to before we see the runway, or 550 meters is our minimum visual reference. Now, if something goes wrong, someone might drive onto the runway, for instance, or an aircraft landing before us or taking off before us for some reason may not clear the airfield in time. So we have what's called a go-round procedure, which is actually shown here by the dotted lines. And so that's in the event of what we call a go-around, we fly straight ahead to 1,500 feet, obviously climbing at the same time, and then left to Backer, which is this VOR here, to maintain 3,000 feet. We've got a plan view of it here where we can see, so we come straight ahead to 1,500 feet and then turn left, go back towards this beacon. Now if that was to happen, radar may give us radar vectors to come back in for another attempt at the runway, or alternatively, if there might be another aircraft behind us and landing, in which case it's not possible to do that, there is a hold at Backer, so if necessary we'd have to take up this racetrack pattern, and we'd have to, obviously we're coming in the wrong direction at the moment for the hold itself, so we'd have to take up a join and then join the holding pattern until radar say it's okay for us to have another attempt to land at the airfield. Now this particular aircraft is capable of landing the aircraft on its own with us monitoring the systems, but today Ed has elected that he's actually going to fly it using the autopilot initially, and then just based on the flight director, but he's going to manually land the aircraft at Gothenburg. And then he'll be taxiing the aircraft off to our stand. Okay, this is a landing card which gives us various speeds that we can't go below unless the aircraft is in a certain configuration. And when I talk about configuration, I'm talking about the set of flaps and leading edge slats. Obviously, we need certain speeds or certain minimum speeds in order to ensure safe flight for the aircraft, because clearly if we go too slow, the aircraft doesn't want to fly. But having said that, we can't land at a speed obviously that's too fast. So we have to gradually reduce our speed, extending flaps and slats on the aircraft to make sure that we can land safely. The flight engineer has completed this for us based on a landing weight. We're going to Gothenburg. The temperature there is 0, the dew point is -1, and there's a pressure setting of 1001. When we fly flight levels, which we're doing at the moment, we have a standard 1013, but we need a reference to sea level pressure when we land, which is 1001. And when we get cleared to an altitude rather than a flight level, then we will change to 1001. We have a marker altitude, which, as I said, was a final approach fix, 1,680 feet. The wind at the moment is very light, it's 100 degrees, it's only 2 knots, and we're using runway 03. And our gross landing weight is 256,000 pounds. And as I said, these are the various speeds that we need to slow down through with the flaps and slats. And then we have a minima, 680 feet, that's our decision altitude, 550 meters, horizontal visibility. Okay, I'm now going to go, we'll set our instruments up with all these speeds, and you'll be able to monitor that on the airspeed indicator.
Landing flight sim on computer.
From the top, 199, 179, 159, 129.
Speed brackets.
only if it's interesting. Well, here we are now at Gothenburg. You may have realised that in fact we landed on runway 21 at Gothenburg and not 03. 03 was the runway that we briefed for, which was the runway that they gave on the ATIS as current at the time. But in fact, because of lack of traffic, other traffic that was around when we came in, and we were coming from a direction that made 21 a better runway for us to land on, and there was a very, very minor tailwind component, we were able to accept runway 21, so in fact we came straight in and were cleared to self-position on the localizer for the ILS for runway 21. So although we briefed for runway 03, we took 21 and Ed gave a brief update for runway 21, the go-around procedure, etc. For runway 21.
Master warning panel. Transponder steaming. Cabin notification and lights. Lights partly square. Radar. Engineers check complete. Configuration test check. Flaps, lamps, speeds. Water brake on throttle. Take our checklist complete. Stabilised. One of this alright?
Oh, I haven't done that. I don't think we've actually looked at this. 311?
Oh, yeah, sorry.
1,000 above? 307? Oh, is it?
Don't we? Marshalling your bed all day.
Okay, this is the pilot's instruments of the Airbus, and they are absolutely standard. It's the standard instrument T. The flight system is probably as sophisticated as an analog style needles device can be. We have the airspeed indicator doubled up with the map meter, the compass display and repeaters. This one shows the VOR DMEs as well. This is a repeater with the ADF needles on. Most sophisticated clock I've ever met, which has time, elapsed time, and we have our own little stopwatch. If we have any malfunctions with the artificial horizon, as we call it, an ADI, or the compass, which we call the HSI, then all of those can be switched over down here to make the aircraft totally safe and redundant. Each pilot has a weather radar, but we don't have any weather, so I'll give you a reflection off the ground. And if this were clouds, then green clouds are a little bit bumpy clouds, yellow clouds are quite bumpy clouds, and red clouds would be very bumpy clouds. But as I say, that's the ground reflecting to give you an impression. The engine instruments are in the natural sequence. With the Airbus, we fly the aircraft principally on N1 settings, which are these. We obviously need to know about the health of the engine, which is reflected principally with the EGT, exhaust gas temperature, and the N2, which is the compressor of the core engine. And beneath us we just have a fuel flow gauge, which is of performance interest. These instruments here are just backup panic instruments, so they're a little baby artificial horizon, an altimeter, and a very simple airspeed indicator. The panel down here is fortunately blank. That's a very good thing, because this indicates a system malfunction, and that will be repeated on the engineer's panel in more detail, but it warns the pilots of a hydraulic failure somewhere in the hydraulics, or that something has failed. The top panel is very, very simple. Because the pilots need to know about the flying controls, they have control of certain flying control functions. The pitch, feel and the rudder travel are there to stop us overstressing the aircraft, and we can manage without them. The yaw dampers are for comfort, and they don't really affect us at this level, and the pitch trim enables us to trim on the thumb wheel, and for the autopilot to trim the aircraft as it's doing at the moment. We come down to the glare shale panel, which once again is very simple. VOR and ILS boxes on each side, and the flight system and flight director system are all combined in these selectors. The selections made on these buttons are reflected in this performance panel if they are successful. Now at the moment we're flying in nav, which is where the aircraft's GPS is connected to the guidance system. Speed select, because we're limited to our speed, the engines would take us well through our maximum speeds. And alt, because we're flying at a fixed altitude of 280. Because the auto flight system is doing all that, it also says command. green functions are things that are actually holding the aircraft under some sort of control. Later on the approach into Göteborg, you'll see amber functions in here, which are warnings of things about to happen. For example, we want to find the localizer, but we haven't found it yet. It'll be amber. When we find the localizer and fly down it, it changes to green. Moving back through the panel here, we have two Lytton INs which we could use to navigate the aircraft, but the GPS is the official high performance device. The central quadrant area here has the speed brakes, which when in the cocked position act as lift dumpers on touchdown, the two throttles, and here are the reverse selectors. Immediate engine shutdown drills sometimes require the fuel to be turned off, and these are done here. We have 3 VHF boxes, 1, 2 and 3. 2 transponders which will be shortly equipped for TCAS. The mod is half done. I think it requires another day in the hangar. And 2 ADFs. As far as we're concerned, at the driving end, the worst thing to happen is a major mechanical failure of an engine on takeoff, and a combination of throttle, fuel lever, and on the roof we have identified grab handles which also arm the extinguishant. And I think that just about covers the basics of the flight deck. Now Ralph Lawton will quickly run round his panel on the engineer's seat.
Hello, I'm Ralph Lawton, I'm the Senior Flight Engineer on today's flight, and I'm going to give you a short guided tour of the engineer's panel. We'll start down here at the constant speed drive unit oil temperatures, both inlet and outlet. As you can see, this one is running slightly warm. This machine converts the variable RPM of the engine into a constant RPM, which we can use for our generators. This is the 2 generators we're presently using, okay, and they provide all the AC electrics right up to this point, okay, for driving all the different systems on the aeroplane. We then get to DC electrics, which are powered by transformer rectifiers, and we also have batteries for standbys in emergencies. Okay, and this is a pictorial of my electrical system for this aeroplane. All the engineer's panels is broken down into subsections, and this is the subsection now for the fuel. As you can see, we've burnt just over 11,500 pounds, or just about that much, and this is the fuel pumps. We are feeding fuel now from the inboard tanks out into the engines, okay, and as you can see, we've got 18,400 and 19,000 pounds respectively to be fed, and in the wingtip tanks we have 7,700 approximately. We'll go upwards from here, and this is a subsection for the hydraulics. This is the quantities of the hydraulics. These are the hydraulic pumps, and the engines drive these pumps mechanically, and this shows me the pressure being distributed from each of the pumps. We have electrical pumps as standby, and also hydraulic to hydraulic pumps, which are called power transfer units. On this aeroplane, this one happens to be inoperative, which is permissible. Up here we have the passenger oxygen system, which I can either activate in the automatic mode, which it's selected in, or by selecting manually, and this shows the pressure of the oxygen system to provide crew with oxygen in the event of a malfunction. Now come on to this panel. This is just a duplicate of the captain's undercarriage indicators. Then when we get on the ground, because of the high energy dissipated through our carbon brakes, I have monitors to monitor for brake temperatures, and if they get very hot, the warning lights will come on. Down the back of the aeroplane we carry all sorts of freight, so in the back of the aeroplane, this small unit here will detect any smoke in any 3 of the compartments that's set up. Here we have agents for firing into the forward and mid compartment in the event of fire in those compartments. This detector loop detects fires and overheats in the engines and the APU system. This little subunit here is our auxiliary power unit, which provides us with high pressure air for starting the engines and emergency electrics through a generator. These are the secondary engine instruments. The primary ones you've already seen on the captain's side. This tells me the temperature of my nacelles. This tells me my oil pressures, my oil temperatures, my oil quantity, and my fuel pressure being delivered to the engine. Okay, we now come on to the pressurization system, which comprises actually of all this area here. Air comes from the engine, and it's depicted here by these lines, through, shows me the temperature of the air coming out and the pressure, into an air conditioning pack, of which we have 2. Okay, then we have a pressurization system, and at the moment I'm using system 1. System 2's on backup. We're presently flying at 28,000 feet, but from my instruments I can tell that we have a cabin of just under 4,500 feet and a pressure of 8 psi. Up here are the selectors for the flight deck, forward cabin, mid cabin and aft cabin, from which I can select the temperature I require. Usually we have these very cold, but the aeroplane is quite empty today, so we have not a lot of, we have a reasonable temperature. Here again another smoke detecting system, but this time it's for the back end of the aeroplane as opposed to this one, which is the underbelly side of the aeroplane. So each one of these can tell me whereabouts in all the different selected areas there is smoke. Up here is a failure detection system. As you can see, none of them have failed, but it will tell me any malfunctions through these magnetic indicators. Okay.
3 minutes.
This system tells me all the doors are closed, all the doors, hatches, interconnecting doors are all closed in the aeroplane, and in the event of a door coming open, I can identify it quickly. This just is a part of the flight deck recorder system. All aeroplanes have to have them. Data recorder, flight deck recorder. This is a multitude of probes which we have outside the aeroplane, and because the outside air temperature is -55, they all have to be heated, and these are very important probes, and therefore they are all individually indicated. Again, because of smoke and fire down the back, this is my test system, which works in coordination with this for me to identify if there is a failure in the smoke detection system. As you can see around me are circuit breakers for many different electrical loads and components, and the same on the top panel. All these are identified in blocks of engines, air conditioning, flight controls, lighting, APU, hydraulics, fuel, and then we come down here to the anti-icing system and ventilation, and finally right beside me down here the electrical power and distribution system. And I basically have to know where most of these circuit breakers are in the event of emergencies. Similarly, up on this panel we have mainly the radio and navigation equipment, but also the minimum equipment supply. These are our last ditch vital electrics in here. And that comprises the engineer's panel. Of course, my responsibilities don't end with this panel. Monitoring the pilots and primary engine instruments is also my responsibility.
Okay, we're just going to run through some of the instruments again, showing you exactly what they're telling us at the moment. At the moment I'll just start on the right hand side here. We're actually at flight level 310, which to all intents and purposes is 31,000 feet. And this is based on what we call the standard setting of 1013. And if all the aircraft that are within the area are on 1013, then with the various vagaries of the pressure in the air that we're going through, they will all be going up and down at the same time, and therefore we will always have the clearance between the various aircraft that we need to maintain. So we're at 31,000 feet effectively, and as you can see from the what basically is an artificial horizon, the ADI, we are wings level. We've got just a little bit of pitch, probably about 1 degree nose up pitch, which the aircraft at this weight with this power setting needs to maintain level flight level. Now our speed, just coming over to the left on the airspeed indicator, it's actually indicating about 294 knots. Now because we're at 31,000 feet and the air is much thinner up here and the density of the air is different, this actually tells us lies, it doesn't tell us the truth. Our true airspeed, which I can take from another instrument, if I can just bring you down to this part of the instrument panel, is actually 466 knots. So as you can see, we're showing 294 and this is 466, so it's actually not telling us the truth. Now what we're doing, because we're at flight level 310, we're actually flying on a Mach number, and at the moment we're flying virtually at decimal 8, which is 8/10 of the speed of sound, up where we are at minus 52. As the temperature of the air changes, so the speed of sound changes, but that's what we're flying on is decimal 8 at the moment. I can bring you down to the HSI, which is our compass system, and we can see here that we're actually on a track of about 225, and as you can see that's magnetic. Now to assist us in our navigation, we're using a GPS system, a global positioning system, using satellites, and there's a small switch just to the right hand side of the HSI, and you can see that GPS is illuminated. Now that tells me that my HSI is now tied in with the GPS system on the aircraft, hence it's showing our track on this lubber line. It's perfectly in line with the 4.5 lines on the orange bar. If we just come to the left, this is our flight director and autopilot indication system here, and we can see that we've actually got nav selected in the auto flight system, and so we're navigating on the GPS. It's also, just while we're up here, we also have speed select, which means that at whatever speed I select this, what we call a summon bug, the little orange bug, then the auto throttle system on the aircraft will follow that bug. So if I reduce the summon bug, the throttles will retard and the speed of the aircraft will reduce, and vice versa. And because we're cleared to flight level 310, and we are at 310, then we've got alt, so we know that the auto flight system is holding it in the altitude mode. We've also got some backup navigation equipment here just to the left. This is an inertial navigation system which we can use instead of the GPS, but the GPS is the primary navigation aid for the aircraft, and so that's what we use, but that's purely as a backup system, but it's useful for an instant readout on the wind, on drift angles and such like. We've also got ground-based beacon information. This is a VOR. At the moment, because we're actually running on the GPS, we aren't flying direct to a ground-based beacon, but if we were, then we could tune it up here and it would give us the track to the beacon and also a distance. Just coming over to the right hand side, we've got our vertical speed indicator, which is reading 0 because we're flying straight and level. There's a TCAS flag here. From the 1st of April this year, aircraft won't be allowed to fly within Europe unless they have TCAS fitted. TCAS is a traffic collision and alert system. Most of our aircraft have got them on the A300 fleet, but this one, the fitting has yet to be completed, but that will be done in the next few weeks. And then further right we have another ground-based navigation system, ADF. This tracks non-directional beacons on the ground, but again, because we're not actually using those to track, then we're not using that, therefore the needles aren't pointing in the direction we're going. But the compass card is always tied to the 3 compasses.